A very good evening to all of you. At the outset, let me thank Dr. Muralidhar and the IAPTA team for their unyielding and untiring, I think, enthusiasm with their academic excellence, and even during these trying times, especially the COVID times. And I thank them for giving me this opportunity to be with this academic event. I've got nothing to declare, and in the next 15 minutes, we'll be talking about the basic principles used in the hemodynamic measurements using echocardiography, and especially the transistor echocardiography. And because of the paucity of the time, we'll try to just enumerate some of the hemodynamic parameters that can be measured using the echocardiography. The basic steps that we use in measuring the hemodynamics using echocardiography. We use the two-dimensional echocardiography for measuring the diameter, the radius, and then calculate the area. We use Doppler principles and the Doppler echocardiography for measuring the velocity of the blood. And then from the velocity, it will be traced or plotted against the time to get the velocity time integral. And from the velocity time integral and the cross-sectional area, we'll be able to calculate the stroke volume. And from the stroke volume, this is included, or rather put in the continuity equation, which follows the law of conservation of mass. And then we'll be able to calculate an unknown orifice area. And the last one is the Bernoulli equation, where the velocity can be used, putting in the Bernoulli equation for calculating the pressure gradient across some of those stenotic area valves or the orifices. Now, if you have an orifice with known cross-sectional area, and if you have a continuous flow, a streamlined continuous flow with a flat velocity profile, and if you can measure the velocity across these, the flow, then the flow rate can be calculated by multiplying the velocity with the cross-sectional area. This is not as simple as this, as told earlier, when it comes to the cardiovascular system, for many reasons. The most important reason is that the variability of the flow pattern that happens within the cardiac chambers. Even though sometimes when it is laminar, it can have a parabolic profile which changes when it enters into a narrower chamber, it becomes a flat profile, then back to a parabolic profile, or sometimes when it goes through narrow orifices, it becomes quite turbulent as well. Another aspect is that the flow is never continuous. The flow is pulsatile or it's phasing. So either during systole or diastole, the flow, and you can see the velocity also increases, reaches a peak, and then comes back to the zero level or the base level. Now we use an echocardiographic probe, either transesophageal or transthoracic, for aligning the Doppler ultrasound beam almost parallel to the flow velocity vector. And the machine calculates what is known as a Doppler shift, and then it gives us the value of the velocity. Now this velocity, which happens throughout the phase of this ejection, either during systole or diastole, can be plotted against time to give you what is known as spectral trace, and the area below or under the curve gives you what is known as velocity time integral. Velocity time integral is nothing but the stroke distance, or the distance the column of the blood will move during the period of that ejection through that cross-sectional area of that orifice. Now, once you know the velocity time integral, and if you can measure or calculate the cross-sectional area of the orifice through which it flows, you can calculate the flow that happens through that, which is nothing but the stroke volume that is happening through that cross-sectional area. Now, once you get the stroke volume, it can be put into the continuity equation, which follows the law of conservation of mass, which states that whatever enters into a closed system of flow has to exit the system unless otherwise something is added or something is removed from the system. Now, this can be put into use in the clinical scenario on the left side of the heart, in the right side of the heart, or between the left and the right side of the heart, including the lung, provided there is no AST, VST, PDA, or any aorta pulmonary collaterals. So if you know the cross-sectional area of one of those valves and the velocity or the velocity integral through that valve, and if you can measure the velocity and the velocity integral to another valve, the cross-sectional area of that particular valve can be calculated using the continuity equation. Now, the same continuity equation can be used in another method, which is known as a proximal isovelocity surface area method of calculating an unknown orifice area. This is not actually the rounded flat pizza, but it looks more like in 3D, more like a hemispherical cassata ice cream, if it is cut in cross section, this is what you see in the echocardiographic screen with the color flow Doppler being displayed. You will be able to see isovelocity shells, which are represented by different colors. Now, the shells at the distal shells, as the proximal, will have the lower velocity, and the shell at the center, that is close to the orifice, will be having a higher velocity. Now, putting this into a clinical context, now when the blood is flowing through a narrowed mitral orifice from the left atria, you can see the blood converges into this narrow orifice. Now, because this blood actually follows the Barth rule, and you have the transducer now in the esophagus, and the flow is happening away from the transducer into the mitral valve orifice, the color has to be blue. But you can see that we saw that earlier, the velocity will increase as it reaches the center of the mitral valve orifice. Now we can see that the color changes from blue through yellow, orange, and to the red. That means the velocity has increased and it has reached the Nyquist limit, leading to aliasing. So this can be seen. This is what you get in the atrium in mitral stenosis. But you can see the similar thing happening in the left ventricle in mitral regurgitation. Now, this particular proximal isovelocity shell can be delineated quite clearly by adjusting the velocity baseline, the scale, velocity scale, by adjusting the baseline of velocity scale. So you will get what exactly is the aliasing velocity of the most proximal shell. That becomes quite clear. Here, it is 0.55. That is the velocity of this particular shell of aliasing shell, proximal velocity. Now, that was seen in the mitral stenosis. Now, when you go to mitral regurgitation, it happens from the left ventricle to the left atrium, and then you can see that the flow is changing from red to blue. But in this scenario, you saw that the color was changing from blue to red. Now, you know that what is the aliasing velocity of the most proximal clear isovelocity shell. Here, this is 45, and you can measure the PISA radius, and this can be put into the continuity equation. Now, you know the radius of the shell, and you know the velocity of the shell, which is the aliasing velocity. Now, the area of this particular hemisphere can be calculated by the equation 2 pi r square. Now, the product of this 2 pi r square into this aliasing velocity should be the same as the effective regurgitant orifice area, which is unknown to us, plus the peak mitral regurgitation jet velocity, which we can measure. So if you know the 3 parameters of the four parameters, the unknown 4th parameter, which is the effective regurgitant orifice area, can very well be measured using the continuity equation. Now, we assume that the hemispherical shells are formed over a flat plate, but in clinical scenario, it is not a flat plate. You can see the mitral leaflets form an angle, but still the PISA is formed. Now, you can measure this angle between the leaflets because it's not a flat plate, and the measurements that you take is based on a flat plate, and this can be put in the correction fraction, the correction equation here, as the alpha angle. So the angle that you measure is the alpha angle. So it can be put as a correction factor in the continuity equation to calculate the unknown area. Now, this particular picture will be quite familiar to all of you. This actually describes about the Doppler principle and the Doppler shift. Now, putting that into the clinical context, we use an ultrasound probe as a source of ultrasound wave, and then it is used as a receiver of the ultrasound wave as well. So now when you interrogate a blood flow, in fact, you're interrogating the RBCs, because the RBCs are one which are going to reflect the wave back into the transducer. Now, when the RBCs are moving towards the transducer, the ultrasound waves which are reflected by the RBC waves back into the transducer will have a higher frequency than the transmitted frequency. And this will, again, the frequency will depend upon the velocity of the RBC which is moving towards the transducer as well. Now, the difference between the reflected and the transmitted frequency of this particular ultrasound wave is known as the Doppler shift or the Doppler frequency shift. Now, in this case, it's a positive Doppler shift, but you can see here, when the RBCs are moving away from the transducer, the transmitted ultrasound wave will have a higher frequency than the reflected ultrasound wave. So now when you reduce or when you subtract the transmitted ultrasound frequency from the reflected, you get a negative value. So it's a negative Doppler shift. Now this particular Doppler shift, or known as frequency shift, along with the speed of ultrasound in the tissue and the frequency of the transmitted ultrasound wave with the cosine of an angle theta, is put into the Doppler equation, we will be able to get a representative or the correct velocity of that particular blood flow. Now, what is this angle theta? Angle theta is nothing but the angle which is formed between the flow velocity vector and the reflected ultrasound beam. Now we can see that because it is a cosine, the lesser the angle, or it is more parallel to it, we'll get a higher value, which is 1, and then velocity will be a representative of the flow. But if it is perpendicular to it, where it is a cosine of 90, it will be 0. So something, if it comes to the denominator as 0, the velocity also will become 0. So what is the minimum or the maximum angle that is acceptable to give you a representative velocity? You can see that the cosine of at 15 degrees is 0.96, but cosine at 30 degrees is 0.87. So anything between about 15 degree to 20 degree will still give you a representative velocity of the flow that you're interrogating. Now, to get an accurate Doppler calculations, hemodynamic calculations using this Doppler principle, the Doppler beam should be aligned parallel to the blood flow as much as possible. And you should always be able to interrogate the peak velocity, and that too throughout the duration of the flow, so that you get an untruncated velocity time integral and an average of at least 3 to 4 VTI in sinus rhythm, or 8 to 10 VTI in atrial fibrillation has to be assessed. And then the radius or the diameter or the velocity, all these things should be measured from the same anatomical location at the same time. Now, the second principle that is used is the Bernoulli principle, which follows the law of conservation of energy, which states that in a closed system of flow, the sum of the kinetic energy and potential energy between 2 points at this point should be the same as the sum of the kinetic and the potential energy between at this particular point. Now, in cardiovascular systems, since the assessment is all made in the supine position, the gravity can be excluded or eliminated. And so what happens is here, you instead of the potential energy, use the pressure energy. So the kinetic energy with pressure energy should be the same here. And the kinetic energy plus the pressure energy at this point should be equal to that at this 2 points. So now if you want to get the pressure drop or the delta pressure or the difference in the pressure between these 2 points, you can use what is known as the Bernoulli equation, which is a very complex equation. In fact, it is known as an unsteady Bernoulli equation. It has got 2 components. One is a convective component, which is nothing but a difference between the kinetic energy between these 2 points. And other one is a non-convective component, which has got 2 factors. One is the viscous friction. The other one is known as the inertance, which produces a local acceleration. Because it is quite difficult to measure the non-convective component of the Bernoulli equation and to incorporate this into the algorithm for a routine use, this has been modified to get what is known as the delta pressure, which is equal to 4 V2 square, which is the distal velocity, minus V1 square, which is the proximal velocity. Now, how is this eliminated? Just have a look into that. Now, the contribution from the viscous fraction happens, especially in blood, only if the hematocrit of the blood is more than 75, and if it is passing through an orifice area which is less than 2.5 centimeters square. Both of these values are incompatible with life, and you will not see this in our clinical practice, and so that can be excluded. Now, coming to the inertance and the local acceleration, this happens only when the velocity at all the points that you're measuring is less than 50 centimeters per second. Now you can see that any point, especially in the LVOT, nowhere you will get a velocity which is less than 50 centimeters per second. So in fact, you can consider that local acceleration doesn't happen at any points in the cardiovascular system because of the inertance. So you can eliminate that also. That is how these two the contribution by these 2 factors are eliminated, and what is left is only the difference in the kinetic energy. So what you get is that the 4V2 square minus 4V1 square will be the delta P. Now, this is further simplified to get into delta P is equal to 4V2 square only. So only the distal velocity is included, the proximal velocity is excluded. How can you exclude the proximal velocity? The proximal velocity being quite small when comparison to the distal velocity, and when it is squared, it becomes even lesser. And when it is subtracted, it doesn't make any difference in the value that you get. But it is not true all the time. If the proximal velocity is more than 1.5 meter per second, and if the distal velocity is less than 3 meters per second, as it can happen in case of LVOT acceleration, flow acceleration, with a septal hypertrophy, or when you have a subaortic membrane, or when you use inotropes to come off cardiopulmonary bypass, especially with a good ventricle, have a higher proximal velocity because of flow acceleration. And so then if the V1, in this case, if the LVOT velocity is more than 1.5, you have to include it in calculating the delta pressure. Now, how do you get this value 4 in this? We saw that what included in the Bernoulli equation is only the difference in the kinetic energy. The kinetic energy can be mathematically represented at half mv square, where m is the mass. So here in the blood, the m is actually, the mass is the density of the blood, which is equal to 1060 kilograms per cubic meter. Now, putting 1060 instead of the m, the equation will become like this. Now, the unit of the delta P, or the pressure drop, is in millimeters of mercury, while the unit of the kinetic energy is in pascals. To standardize it, this pascals will have to be converted into the millimeters of mercury. You see that 1 millimeter of mercury is equal to 133 pascals. So you have to divide this 1060 by 133, and you get a value which is 7.96. And half of that, this is still half is still persistent here. So the half of 7.96 will be 3.98, which is rounded out to 4. So that is how you get the value 4. Now, the pressure that you measure using the Doppler echocardiography is actually the peak instantaneous pressure gradient across that particular valve or the orifice for a given velocity. Normally, we select the peak velocity. And so what you get with Doppler is the peak instantaneous pressure gradient across that particular orifice. Now, when this particular pressure gradient is measured in the cath lab, the cardiologists actually, they measure the peak-to-peak gradient, which are not happening instantaneous. They happen 2 different times. And you can see that the pressure gradient measured by the echocardiography is far higher than the peak gradient. It says that the peak gradient is more representative with echocardiography, and the peak-to-peak gradient is more representative of the mean gradient. So with that, the principles that we use. What are the parameters that you can measure using the echocardiography? Now, we saw that we can calculate the stroke volume. From the stroke volume, we can calculate the cardiac output. The cardiac output can be measured both on the right side and the left side, and then you can get the QP, QS if you want. And then you can measure the peak gradient. And then from the peak gradient, you can calculate the mean gradient, which is 0.7 time, or 0.7 is the factor for conversion of the peak gradient to the mean gradient. And using the continuity equation, you can measure the stenotic valve area or the regurgitant orifice area. And then using the Bernoulli principles, you can measure the chamber pressures. For measuring the chamber pressure, you need to have the pressure gradient and also the pressure in one of the proximal or the distal chambers. You can see that for measuring the chamber pressure, there is always a prerequisite for a pathology. For measuring the RVSP, that's the right ventricular systolic pressure, you need to have a TR. For measuring the left atrial pressure, you need to have an MR. And for measuring the LVEDP, you need to have an AR. So to summarize, Doppler echocardiography can be used for measuring many hemodynamic parameters, including the chamber pressures, the gradients, the stroke volume, the regurgitant volume, and all these things can be measured non-invasively. That is the advantage by echocardiography. The principles used are the Doppler equation, the Bernoulli equation, the continuity equation, and the accuracy of the measurements can be improved by making the measurements at the same anatomical location, the same cardiac cycle, which may not be possible all the time, that we know. And some errors can creep in by this. And some errors can creep in, especially when the measurements are made in wrong echo planes, especially when there is foreshortening that's happening. And then we saw that for measuring the chamber pressure, you require some pathology as a prerequisite. But in spite of all these limitations, because of the convenience of non-invasive assessment of hemodynamics, it can help in clinical decision-making and in the management of patients. Thank you very much.